I will present our work on model distributed DNA training for memory-constrained edge computing device. This is a collaborative work with Professor Sefgru, Dr. Dasari, and Professor Kyunju. The traditional approach to distributed deep neural network training is data distributed learning, which partitions and distributes data to workers as illustrated in a master worker setup in this figure. In this setup, the data is partitioned as many times as there are workers in the system, and all workers train multiple instances of the same model on different subsets of the training dataset. The workers apply the same algorithm to different datasets. The same model is available to all workers after update at the master device. Data distributed learning, also called data parallelism, has been frequently used as a de facto distributed learning mechanism in practical systems, especially in multi-GPU platforms. This approach, although has good convergence properties, has high communication and storage cost, which puts a strain especially on edge systems. Excessive communications among computing entities due to frequent weight synchronizations in data distributed learning increase the transmission delay, which increases overall training delay. Furthermore, computing entities should receive and store all the weights, which may not be flexible for large model and computing entities with limited storage. Model distributed learning is an emerging approach where layers or parts of a training model are distributed across workers, as seen in this figure. In this setup, no single worker has a complete model, but it is distributed across all workers. Thanks to distributed model across multiple devices, the whole model does not need to be exchanged among the master and workers, which is promising to reduce the communication and the storage cost. This approach has been frequently investigated in multi-GPU platforms as listed in these works. A challenge of model distributed learning is that it requires to store the multiple versions of the layers weights during the training phase. This ensures the forward and backward propagation phase corresponding to one training batch always undergo the same version of the weight at a given layer or device. Unfortunately, the number of the version to be stored should be proportional to the number of the workers in the system, meaning that the model distributed learning may introduce high storage requirements which put a strain on memory-constrained edge computing device. In this work, we focus on model distributed training at memory-constrained edge computing device. We designed mcPipe to reduce the memory cost of the model distributed learning. mcPipe uses an on-demand weight updating policy, which reduces the amount of the weight that should be stored at the worker. Next, I will present the detail of the mcPipe. We consider master worker topology by D2D connections. Workers may fail or sleep or leave the network before finishing their assigned computational tasks. Also, workers incur a probabilistic delay in responding to the masters, where delay has two components: the transmission delay for exchange data, model, and the parameters, and the computation delay. In our learning model, we have the training set I, the label vectors y, and the weight matrix is w. The goal is to minimize the loss function via a gradient descent-like algorithm. We consider that the training dataset I1 to IM is used to train a 4-layer fully connected neural networks, which has key neurons in each layer, and the last layer is the output layers. Assuming that there are 4 workers in the systems, they collectively train the model W. In the forward propagation phase, a worker 1 will receive data I key from the master device at the tth iterations of the weight update. Workers 1 calculates the A1 KT, whereas A1 KT is the activation vectors in the first layer, and worker 1 transmits the A1 KT to the worker 2. Similarly, worker 2 and worker 3 calculate the AN KT, where the G is the activation functions in this formulation. Worker 2 sends the A2 KT to the worker 3, and the worker 3 sends the A3 KT to the worker 4. This completes the forward propagation. In back propagation phase, worker 4 calculates its error vectors delta 4 KT and sends the delta 4 KT to the worker 3. Similarly, the error vectors of the worker 2 and worker 3 are calculated as the delta n KT, where the dot star is the element-wise multiplications. G prime is the derivative of the G. Worker 3 sends the delta 3 KT to the worker 2, and the worker 2 sends the delta 2 KT to the worker 1. After receiving the error vectors, worker updates their weight matrix. In particular, worker 1 will calculate the weight matrix according to the W1 T plus 1, and the worker 2 and the worker 3 will update their weight vectors according to the Wn T plus 1. This completes the backpropagation phase. As seen, the model is updated across workers in a distributed manner by only exchanging the activation and the error vectors among workers. This approach is promising to reduce the communication cost as well as storage and memory requirement. But it is not working conserving. Pipeline is a promising solution to address this problem by keeping workers busy. Workers process multiple instances of the data, activations, and error vectors. The next examples illustrates the main idea of the pipeline. Let us assume that the last weight update at each worker is the tth update. The most recent weight will be the WNT at worker n. Each worker will process up to 4 activation vectors before a new weight update occurs. Worker 1 will calculate the A1, K plus P, T, and send them to the worker 2, and then it stops and waits for a weight update. After weight update, W1 T plus 1 is done. A new activation vectors A1, K plus 4, T plus 1 is calculated and transmitted to the worker 2. So similarly, worker 2 and worker 3 will calculate the AN alpha beta, and this completes the forward propagation phase. In the back propagation, worker 4 will calculate the error vectors delta 4 alpha beta and send it to the worker 3. The error vectors at the worker 2 and the worker 3 are calculated at the delta n alpha beta. Workers update their weights after receiving an error vectors from neighboring workers. For example, worker 1 will calculate the W1 T plus 2 after receiving the delta 2 K plus 1 T. The general rule is that the most recent weight W1 gamma is updated using the last received error vectors. Similarly, worker 2 and worker 3 update the most recent weight Wn gamma after receiving an error vectors delta n plus 1 gamma and beta. This completes the backpropagation phase. One of the challenges of the model distributed learning via pipeline is that it requires to store multiple versions of the weights. For example, W2T is stored at the worker 2 until the W2T plus 4 is calculated, as the W2T is needed to calculate the error vectors delta 2KT and until the delta 2K plus 3T. Meanwhile, W2T plus 1, W2T plus 2, W2T plus 3 are also calculated as the worker 2. This means that the worker 2 stores the 4 weights from the W2T to the W2T plus 3 until finishing calculates the delta 2K plus 3T. Overall, the number of the weight versions that need to be stored in the worker is partitioned with the min bench size. So in this example, it's 4. And we designed mcPipe to address this issue. The main idea behind the mcPipe is that the weight updates are calculated only when they are needed. In the forward propagation phase of model distributed learning with pipeline, the most recent weight is used to calculate the activation vectors, and in the back propagation phase, error vectors are calculated using the same weights that their corresponding activation vectors will use. For example, a delta 2 K plus 2 is calculated using the weight W2T, although at this time the W2T plus 1 and the W2T plus 2 are available because the corresponding activation vectors of the delta 2 K plus 2, which is A2 K plus 2, is calculated using the weight W2T. So to reduce the number of the weights stored in the workers, mcPipe calculates the weights when they are necessary. In this case, W2T plus 1 is not calculated immediately after receiving the error vectors delta 2 KT. Instead, error vectors and the activation vectors need to calculate the weight W2T plus 1 are stored, which are delta 2 KT and the A1 KT. So these vectors are used to calculate the W2T plus 1 when it needed. A calculated weight matrix is delayed from the memory if no other vectors need to use that weight or there are earlier weights. Thanks to storing only the activation and error vectors instead of the weight matrix, mcPipe reduces the memory cost significantly. In particular, assuming that the total model size is omega, which is shared equally across n workers, If the bench size is m, the memory cost of the mcPipe at each worker is at most omega divided by n plus 2 times m minus 1 times the square root of the omega divided by n, while it is the m times omega divided by n for model distributed linear pipeline. We evaluate the performance of mcPipe on a real test bed and compare to different computing schemes. Our experiment environment consists of 2 computers and 1 MacBook Pro. The computers are connected to the same local area networking using internet cable. We have used the VGG16 as our training model. This is the result of the 2 workers scenario training the VGG16 model for the MNET dataset. Both workers are MSI computers. The horizontal x represents the training time in minutes, while the vertical x represents the accuracy of the training model. We compare the performance of our schemes, mcPipe with different baseline and computing schemes. In particular, local represents the local computing where all the training is performed on one of the MSI computers, which are both faster than the MacBook. Gradient update refers to the schemes that the workers do not worry about the consistency about the gradient update during the training phase. Specifically, when a new update opportunity arrives at any worker at any given time, the worker updates its weight and erasing any previous version of its weight from the previous times. We can observe that both our schemes and mcPipe and PipeDream achieves almost exactly the same performance at all training times. This is expected as mcPipe guarantees almost the same performance with PipeDream, with the extra benefit of reduced storage cost per worker. These figures are for 3 worker scenario where the left figure uses the MNIST and the right figure uses the CFR10 dataset. As seen, mcPipe has similar performance with PipeDream with the extra benefit of reduced storage cost per worker. To conclude, we investigated the model distributed in training for memory-constrained edge computing device. We designed the mcPipe, which uses the on-demand weight updating policy to reduce the amount of the stored worker. We implemented the mcPipe in a real test bed and showed it is improved the memory cost without hurting the convergence rate.